book is yours.
Okay, thank you so much, Joaquin. Thank you, everybody, for being here, for inviting me to give this talk. And yeah, mainly my current research is focused on blockchain systems in general, and in particular, I work in applied cryptography to these systems. And well, one of the main tools in this context are zero-knowledge proofs. So in this talk that is going to last around 1 hour, so we're going to just give an overview of what are zero-knowledge proofs, some scenarios in which we can apply zero-knowledge proofs related with, in general, with security, but in particular, we will talk also about some scenarios in blockchain. Okay, so and well, you can interrupt me as if you have any questions, you can interrupt me as I just explain things. So no problem. Well, this project is founding my trip here, so I just want to make a photo with this project, and that's it. Okay, so it's a cátedra. Well, it's something. It's some funds to promote cybersecurity. So well, that's it. So well, since I don't really know how much you know about zero knowledge, I prepare an introduction that is auto-contained, and I will explain like everything. I don't assume that you don't know anything. And well, the idea is that why zero knowledge appear? I mean, in general, if we have zero knowledge proofs appear in a system in which you have two entities, okay, a prover and a verifier. Someone is proving something, and then someone is verifying something, okay? If I ask you which is the trusted party here, most of you obviously will say that the trusted party is the verifier, okay? Because, I mean, the verifier is trying to verify something, and the prover is the one that can be malicious in some way, right? Well, zero knowledge proofs ask a different question. I mean, this was like the scenario before zero knowledge proofs, but in zero knowledge proofs, they ask, okay, but what if the verifier is somehow untrusted, or we cannot completely trust the verifier, or what can the verifier do while proving something? Okay, and this was the question that Mikhaili, Rakov, and Shafi Golbasser did in 1985, which is the original, let's say, the initial paper of this area. Okay, and concretely, they ask about how much extra information the verifier is going to learn while you are doing the proof. Okay, this is the thing. And zero knowledge comes from the fact that we want that that the verifier learns nothing else. I mean, learns nothing beyond that the statement that I'm proving is true. Okay, and this is why they call it zero knowledge. Okay, so the information leakage should be zero. Okay, and then, well, we are starting, so we are going to provide one of these classical examples. Okay, and so imagine we have a deck of cards. Okay, it's a poker card, and then I pick just one card. Okay, and I want to make you I want to provide you a proof that I pick a red card. Okay, red card. So obviously I can prove you that I pick a red card if I show you, okay, the card. But then I'm giving you more information. I mean, the statement exactly is I pick a red card. Okay, so if the method that I use to prove you that the card is red is just showing you the card, you are not going to learn only that the card is red. You are going to learn also that, you know, the exact number. Okay. Sorry. So yeah. So then how we do a zero knowledge proof here? I don't know if anybody has an idea, but Joaquin, any idea?
Not yet.
Not yet? Well, then I show you all the black cards. I think poker has 49, I think 49 cards, if I'm not wrong. No, 52, right? 52, right? So if I show you 26 black cards, you don't know which red card do I have, but you know that I have a red card, right? So this is a zero knowledge proof, okay? And things like that is, I mean, this topic started like this. And we were building, the next question that I'm going to ask is, well, how can I build zero knowledge proofs, okay? And at the beginning, zero knowledge proofs were like very particular for each thing that you wanted to prove, okay? So, and there were a lot of, I mean, I can prove you that I know the, I don't know, some I know the discrete logarithm of this number in a group, or many specific statements, okay? And I think that the great revolution in the area came when people started to think, okay, how can I prove a general computation? Okay, so how can I prove general things from computation? Okay, and in this particular, well, in this setting, we can define computation. We can define computations in two ways mainly. Okay, the first one is circuits. We can define a computation as a circuit, and I'm going to provide you an example of a computation that is modeled as a circuit. I think this is like the biggest change in the area of zero knowledge, because when people started to see how to, I mean, I need to take my problem that is a computation and I need to build a circuit, okay? And then the circuit is modeling my computation. And then from there, I have like, this first step is what we call the front end. And the idea is to arithmetize my problem and convert this problem into a circuit. And then this is the front end. And then I just apply some cryptographic techniques, which are the backend, and generate a proof, okay? And this separation is very good because there is people now that can focus on modeling their problems as a circuit, and then there is like machinery that can generate the proof, okay? So
the circuit, so we see this one here, but you mean in general satisfiability circuits for computation in general?
Well, in fact, what you prove is that you know the values of all the wires in the circuit that satisfy the circuit. Typically, you always, the output is, well, you can do this in several ways, but one way is to put that the output is 0, because finally you subtract what you expect. So you can model this as a satisfiability problem of a circuit.
What's the purpose of the circuit? To prove some properties of the computation you are working, or what's the purpose of the circuit?
The circuit can, I mean, the purpose of the circuit is to prove some computation, yeah. And then you can, these things here, we can think as the inputs of the circuit. And then you can think that this is like the output of the circuit, okay? And then here you have a value, okay, that you are subtracting, and then this gives 0, okay? So and this value for this is going to be public. I mean, this is also, you're going to provide also this value, for example, or maybe, I don't know if this example is very good. Maybe one of the inputs, in fact, is an output, and we are just putting it here. And I mean, you can model your circuit as the final result is 0, or the final result is some number. Okay. Yep.
The circuit, is it known by everybody, or is it like a black box, and you check that the result is okay? How does it work?
Can you repeat the first part of the question?
Is the circuit a black box, or the one you want to verify, or is it, or do you know the full structure of the circuit?
In these problems, you know the full structure of the circuit. And the only thing that you can change are the inputs. Yeah. Okay, so a computation is a particular circuit with a particular structure. Okay, and our circuit, I didn't mention, but the circuit has gates. This is called gates, and that we can multiply and sum. Okay, this is these two arithmetic operations. Okay, this is one way. And yeah, the main revolution in the area of zero knowledge, I think it came when people started to generate systems to prove computations modeled as a circuit. Okay. And I'm going to, give here some example and let you know a little bit how it works. Okay. This is one way. The other way is to think as, and I'm also going to provide some examples about this other model, is to think that the computation is modeled as a state machine. Okay. Some authors like to say that this is also a circuit in somehow it is also a circuit, but it's a structured circuit, while they call this a structured circuit. Okay, in circuits, when I say circuit, I mean there is not fixed structure. I mean you can connect the gates as you want, and in each stage you can have more or less gates. There is no fixed number of gates in each stage, let's say. On the other hand, in the machine model, there are a fixed number of values, okay, and then there are some rules that make the state change, okay, but the number of columns that we have here is like fixed. It has a structure, and well, we have to decide how many columns do we put in our in our design. We need to decide the number of columns essentially, okay. And then we need to decide also the rules that make change from one state to the next one. Okay, so well, at this moment, it is just a very general idea that we can model the computation as a circuit or as a state machine. Okay, the idea of the talk is to give examples of the two models. Okay, so let's start with some circuit-based approach. Okay. By the way, I'm going to stay only in the front end in this talk. Okay. So I'm not going to very specifically talk about the backend that allows to prove any of these two computations. I'm going to just show you how to model a computation as a circuit or as a machine. Okay. We have many different types of backends, in fact. Okay. So then, as a circuit, we can model the following statement. Okay, I want to model the following statement. Okay, and I'm going to do a circuit that is not 0. Okay, I'm going to create a circuit with a certain output that is different from 0. Okay, but I'm going to put this out into the statement. Okay, I say that the out of the computation should be 1 if the first input, I mean, I have a circuit here, and I have two input values and two signals. It's typical to call signals to the wires of the circuit, is one name, wire or signal. Well, I have two signals here, and these two signals are like OR here. We have an OR here, which means that, well, this wire here is going to be 1 if any of them or both are 1. Okay, so this is like an OR gate here. Okay, to give a little bit more, well, to put it like a practical example, for example, S1 is a signal that means that if someone is the leader of a group, okay, you can be the leader of a group. Then if you're the leader of a group, then S1 is going to be 1. If not, you're going to be 0. Okay, then you may be a manager, which is a bigger, let's say, a bigger role. Okay, so if you are the leader of a group or if you are a manager, this one is going to be 1. If you are neither of these, then this is going to be 0. Okay, and then S3 is another binary. I mean, here in these signals, I'm just using binary. I'm using S1, S2, and S3 as binary wires. Okay, this can only take values 0 and 1. Okay, in general, these wires can take values inside a field. Okay, a mathematical field with sums and multiplications. Okay, but here I'm just using binary values. Okay, so S3 means if you belong to a certain department. Okay, so if you belong to a certain department, if you don't belong, this is going to be 0. If you belong, this is going to be 1. So finally, the out, in some way, out equal to 1 means that you are a group leader or a manager of a certain department. Okay, if not, the output is going to be 0. So it is a very simple binary logic here. Okay, and I want to generate, I want to generate a proof for this circuit, okay? And yeah, S1, S2, and S3, these are going to be the inputs of this circuit, okay? And then I would say here we have 3 inputs and 1 output. Okay, it's easy. Okay. Okay. So now to well, this is a circuit, okay, but I need to the proving system needs, the idea finally is that the proving system, what it does is to check a bunch of equations, okay, that signals must fulfill. Okay, so which are these bunch of equations here? Well, to make it simple, I'm going to use, if you know a little bit of electronics, maybe you know that the NAND gate is a universal gate because you can build any other gate with the NAND, okay? And well, the NAND has the truth table that, you know, well, let's put it here, but anyway, well, you can transform these, well, let's put it S1 and S2 and out, okay? So 0 is 0 is 1 because it's a NAND. So 1, 0, this is 0, right? Okay, this is the truth table of an AND. Okay, I'm doing it right. I'm something wrong? No. Okay.
Need to go back to my.
Well, it's just I mean it's an AND. Okay.
Yeah, the opposite.
But then the opposite. Okay, so 0 with 0 should be 0 and this 1. Okay, so this is the NAND. Okay. But here we have an equation also. Okay, the equation is that S out, in fact, is 1 minus S1 times S2. Okay, if you, yeah, you can go from the table to this equation here. Okay, you can check that if S1 and S0, if any of them is 0, then the out is 1. But only in the case that S1 and S2 are 1, then the out is 0. Okay. So the thing is that the previous circuit can be, we can use this other circuit, which is based only on NANDs, okay? So this is the OR, okay? Building an OR with NAND gates is this equation here. And, well, building an AND is just, you know, putting an NAND here and then negating, which is this way, okay? So, and since I know the equation of one of these, is just this bunch of equations, okay? Maybe it's not so important that, the only thing that you may remember here is that I need, I need to build a circuit. I need to somehow create all the equations that define this circuit, and these equations and the proving system, the backend, what it does is to efficiently prove that all the signals fulfill this equation, okay? And that's it. This is the idea, okay? And this is like this could be like the last part of our circuit, okay? But in general, what you could do here, more cryptographically speaking, and I'm not deploying this logic because this circuit is much bigger. Okay, I just explained in the last part of the circuit, but in general, we could build a circuit like this, in which you just put a public key. I assume that you know a little bit of cryptography. Okay, so here you put the public key. I mean, you have a credential. Okay, you have a credential in your it's a signed credential. Okay, there is a public. I mean, there is a secret key that signed this credential. Okay. And in my credential, it says which is my department and which is my role, right? So then we can input here in this circuit, we can put as an input well, this is a technical stuff that you always need to put the first signal that you put in a circuit always is a 1. Okay, well, it's a technical stuff. But in general, you put here the public key of the issuer of the credential. You put here the identifier of the sales department, and you put here your credential, your signed credential. Okay, these are the inputs of the circuit. Okay, and then there is a circuit here that is decoding there. Is checking that checking that the credential is correctly signed by this with this public key, and is checking whether you are from, if the credential says that you are from this department or not, and so on. And then this circuit outputs these three wires here that are just telling us if we are a leader, a manager, and if we are a manager or a leader from which department. Okay, and then we have the output of the circuit. Okay. Yeah, I did the easy part. Okay, this is much difficult here, but you can imagine that you can build a circuit that checks, that computes this thing. Okay. Another thing to notice here is that I'm putting things in green and things in red here. Okay, and this is because in zero knowledge, well, I remember that I wanted to prove something, and we should, when you are dealing with zero knowledge, you always need to write very precisely which is the statement, because you just want to prove the statement. Okay, and the statement here would be I have a credential. Okay, signed by this public key, well, signed with the secret key associated with this public key, okay, that says that I'm from department, I don't know, an identifier, 1, 2, 3, 5, I don't know, whatever, okay, and that I'm a manager, or a leader. Group leader. Okay. But the statement says I have a credential. It doesn't say anything that I'm going to show you this credential, right? So the credential, as you see, is what we say a private input of the circuit. Okay. So, well, there was a question about the circuit. The circuit is fixed. Okay. The computation, the thing that I'm going to do is fixed. When you build, you can create different circuits, but then it is another circuit. Okay, you can create different circuits for different computations, but each circuit is defining a specific computation and has a specific shape, and the only thing that you can change are the inputs. But what we are seeing here is that we can have public or private inputs. Okay, when you are using zero knowledge, you are using private inputs. Okay. If you are not using any private input, then this technology is still very useful. Okay, so in general, it happens the same as in blockchain. Okay, blockchain is just a way of building a distributed ledger. In fact, the topic is distributed ledgers. Okay, but blockchain is a way of building a distributed ledger, and blockchain is like the marketing name. Zero knowledge is like the marketing name here. Okay, 1 second. But you can build with zero knowledge technology. You can also implement other scenarios like the following one. If all the inputs are public, there is nothing secret there. There is no way of leaking anything because anything is public. And then, but you are using the same technology to prove that the computation is well done. Okay, because the thing here is that the proof is much faster to verify than running the circuit. Okay, and then I give you the flow for the question, but then you should call these verifiable computations. Verifiable computation. Okay. So verifiable computations are also implemented with zero knowledge technology, but in there we don't have any privacy issues. We don't care about anything private. Everything is public. Okay, but the technical name should be verifiable computations, But you will see in the research and also in the industry that many people is using the term zero knowledge anyway, despite there is nothing private, nothing to leak, nothing to protect, because all the information is public. Yeah.
Something like that.
Okay.
So if I get it right, all these circuits sit with the prover, right? And the only thing that you give to the verifier is the output.
Not. I'm going to go into these details. Maybe it will be more clear. I didn't. Yeah, this is like the concept right now. I'm going to, in a next, you will see what the prover does, what the verifier does. Yeah, your question is normal at this point, but ask me again if it is not clear. By the way, should I maybe I should, Christina, maybe I should say again the question. I don't know if for the people, well, she's asking about what does the prover and what does the verifier. Okay, so we're going to see it in a moment.
How does the verifier know that I really do have the credential? This is what I need.
Okay, because, well, let me put it. Let me draw it here. Okay. So it is because I was going to explain what the prover and what the verifier does. But I was going to explain this with the other model, but also applies to this model. Okay, I just wanted to go through circuits quite fast to go to the other model. But anyway, I think we can do it. The thing is that I have the prover. Okay, so the prover and the verifier both agree on the statement computation circuit. They are synonyms. Okay, finally, we have some statement that finally some computation, and we need to transform this into a circuit. Okay, so finally they agree on a circuit. Okay, well, the people here like to put like this C. Okay, so we have the shape of the circuit is fixed and is known by prover and verifier. Okay, and then you can imagine that this circuit could be huge. Okay, it's a lot of gates. I don't know. We have circuits of hundreds of millions of gates easily. Okay, in typical scenarios and in scenarios of blockchain, for example. And the thing here is that the prover, I mean, the verifier wants to verify that if you put these inputs, let's start with all the inputs public. Okay, let's do a pure verifiable computation scenario. Okay, so all the inputs are public. Okay, and the circuit is known. So one way to check that the output is correct, the verifier could execute the circuit, okay, and see that if I put this input, I get this output, okay. But this is not the idea here. The idea is that the verifier can verify that the output is correct, but doing extremely less work than executing the circuit, okay. And this is the idea of these new systems of zero knowledge. I mean, it is not only zero knowledge. It is the thing is that these systems are succinct, meaning that the verifier can verify that the computation is well done, that the circuit is satisfied, that the output is correct, okay, with a very small amount of bytes, okay, in the good systems with only 200 bytes, for example, and with a few microseconds, okay. And what I'm going to provide you, and the prover, well, the prover has much more work. The prover has more work than just running the circuit or executing the circuit. The prover has to generate the proof, so has more. I mean, we are doing here an asymmetric scenario in which the prover has much more work, okay, but we take work out of the verifier. Okay, this is very good for blockchain because verifiers can be smart contracts in blockchain, which they have a very small, limited resources there, and it's expensive to execute things. So this is why this is perfect for blockchain scenarios. Okay. it is also perfect for delegating your computations to some powerful cloud server, and then it computes and then returns the result. But yeah, I want to make sure that the computation is well done. But you can give me also a zero knowledge proof. Technically, it's not a zero knowledge proof, is there is nothing secret there. So, well, you can give me a verifiable computation proof, but it's used with the same techniques. So you give me a proof. So the prover computes the output and generates a proof. Okay. So what the prover gives to the verifier, the proof and the publics. Okay, and the publics here are all the green things. Okay, so as a prover, I'm going to give you a proof. I give a proof to the verifier. Okay, and I give all the public values, which in this case, I mean, if everything is public, then I give you the inputs and all the inputs and all the outputs. If something is secret, is private, then I'm going to give you only the public things, but not the credential in this case, in this example. Okay, and you are going to be convinced that I will be convinced, if you're the prover, I will be convinced that you have a credential that is signed by this public key, that inside says that you belong to this department, and that is correctly signed. And well, but I will not see the credential. Okay, this is the thing. And here you give the publics. Okay, and the publics, as I said, are public inputs and outputs. Typically, the outputs are always public. Yeah.
For me, it's not yet concrete enough. What is the shape of the proof? What it is exactly? Is it an algorithm? Is it what is it exactly?
It depends. It is a bad question for you. A bad answer. Sorry. It depends on the backend, right? It depends on the backend. Yeah. For example, I don't know if you are for the field of cryptography. It depends on the system. It maybe some systems, for example, build there is a lot of values here. They build a hash tree with them, and then the proof is the root of this tree and some Merkle paths. This is one example. This is one of the backends, which is called Fry. Fry is only based on hash functions. Maybe maybe these are points of an elliptic curve. So here we have two values. It depends on the backend. Okay, there are backends that are based only on hash functions. They provide bigger proofs. They are backends based on elliptic curves. They provide smaller proofs typically. Yeah, the backend is the heavy thing. I thought it was too much for 1 hour. Okay, but well, it's well. I mean, it's a lot of fun. The backend, seriously, I like a lot. But yeah, for this talk, it depends. Okay, but it's something that allows. If, for example, the one with the cryptographic, the one with the elliptic curve, essentially, okay, let me give you. Essentially, they transform the circuit into just a polynomial, and then I show you that I know the polynomial with just letting you that, I mean, then proving that I know that 1 point of the polynomial, one random point, I just do like a random evaluation. I mean, a secret. I do an evaluation of this polynomial without knowing. Well, it's a little bit strange, but there are techniques here to compress the thing. Okay, and mainly all the techniques go from taking a lot of values, convert these, interpolate this into polynomials, build one big polynomial, and then show you that I know 1 point in this polynomial that is correct, and this shows that everything is correct in a very, very high level. Okay, there are a lot of details here. And we can interpolate these polynomials or represent these polynomials with hash trees or Merkle trees, or with polynomial commitment schemes based on elliptic curves. Well, there is quite a lot of technology here to build this thing. Okay, but the amazing thing here is that with a very small proof, the verifier can check that a huge computation is well done. Okay, and even more with some things that are not shown. Okay, with some inputs of the computation that are not shown to you. Okay, so this is the thing. I answered your question, by the way.
For me, yeah.
More or less.
Honestly, the mention of the using hashing function was enough.
Okay.
I can see this.
More or less the idea.
The rest is not my domain. So.
Yeah, it's a little bit difficult to, yeah. Yeah, and I answered you a little bit. What does the prover and what does the verifier?
So in the proof for the circuit includes also the credential verification as a part of the.
Yeah, the credential verification is part of the circuit. The logic of the circuit is verifying the credential. I mean, this part of the circuit is checking that the credential is okay. If not, I mean, if the credential is wrong, maybe, I mean, I didn't polish too much this example, but maybe belongs to the department, I would put it to 0. If the signature is, I mean, I could also add more wires here, signature incorrect or something like that, right? I didn't put too much details here, okay? But yeah, so this logic is decoding the credential and is telling me if it is well signed, if it is from the department and whatever. Okay.
Yeah, and the thing is how to know the circuit, like the prover.
Is because we agree on the circuit previously, okay? And this is yeah, I'm extremely oversimplifying everything here, okay? What does it mean that we agree on the circuit? Well, it means that we both know the shape of the circuit. Then there is a preprocessing of this circuit with some randomness. Finally, there are some random values that represent the circuit, okay? So yeah, everything is complex. If you dig a little bit, then I need 1 or 2 hours for each thing. But yeah, the thing is that we agree on the circuit. Finally, there is a preprocessing stage in which we take the circuit and we do some computations with some random values, some hashing, some stuff. And finally, we have like a few things that represent the circuit. Okay, this is more or less the idea. And these few things, they are also included in the, I mean, when you are going to prove, the prover doesn't need to send these things because we already, the prover and the verifier, I mean, the preprocessing is publicly known and the verifier just uses this cryptographic material that we usually call the verifying key. It's not a key, it's just some material, some cryptographic material for the verifier. So if we take a look at what the verifier does more concretely, okay, the verifier, what it does is to put the proof. The proof is typically, we use pi for the proofs, okay? Put the publics here, and then prove the verifying key. Okay. And essentially this says okay or not okay. Okay. And the verifying key represents the circuit. Okay, but it's a compressed version of the circuit. Okay, again, it's taking the circuit below. It depends on the system. Okay, but typically you take the circuit, convert this into some polynomials, mix this with some randomness, and do some cryptographic stuff that is more or less complex. Okay, and it depends on the circuit. It depends on the backend system to prove. Okay, in fact, what I wanted to show you today is that if you want to use zero knowledge, you don't need to know the backend. I mean, you can say, okay, I model my computation as a circuit, and then there is something that generates a proof automatically if you want. Okay, so if you like applied cryptography or cryptography, then you can go into the backends and see how they work, and maybe you can contribute there. Okay, but yeah, as I said, my topic is more focused on this idea that we can easily, in fact, today, very easily create model computations and then generate proofs. Okay, this is going to be more evident even in the second model. Okay, just 1 second, because in the second model we're going to be able to just create a program, regular computer program, and then we are going to be able to generate a proof for this program. Okay, so you don't need to specify the computation as a circuit. Specify the computation as a program. Okay, and this is the second model. Yeah, sorry for. Yeah. Mm-hmm.
The verifying key, maybe it can be a hash of the circuit. So
more or less is a hash of the circuit.
for me, it's okay.
In a nice way, so that the backend can deal with this. But you're not wrong. It's more or less a hash of the circuit. It's a cryptographic summary of the circuit that is suitable for this backend. Okay. Mm-hmm. It needs to be somehow a hash, because if you change something in the circuit, then the verifying keys should be different and nothing should be right, because, you know, this is, we are generating a proof for this circuit. Okay. And I need to know which is the circuit that I am checking. Okay. I would say that this started in 2009, 2008, 9, 10. For 5, 6, 7 years, we had this. I think that the circuit-based arithmetization of the computation was the predominant one, and then started to appear another way of modeling computations and then proving that. Okay, which is more the machine way. Okay, and in the machine way, we have, remember that we have like each stage is like has the same shape here. We don't have different gates at different. I mean, the machine is just a state machine that is evolving, and the state is defined by a number of values. Okay, yeah, this is a matrix. Okay, essentially, so the computation finally is a matrix, and in zero knowledge we call it the execution trace. Okay, and let me put again a simple example to exemplify an execution trace and see some features of this execution trace. Okay, and I prepared quite a lot of material, I'm saying, but maybe I just going to explain these two stuff. And well, anyway. Okay, so the computation that I want to do is this one. Okay, I want to do X. I want to in this computation I have 3 inputs: X0, X1, and X2, and I want to perform this computation. Okay, X0 plus X1 times X times 4, and then times X2. Okay, this is the computation that I want to do. I can build a circuit to prove this computation, but now I'm going to do it with a state machine, okay, which is different, which is a different model. And in the state machine, I'm going to define, I mean, from one state to the other, we change with an operation, okay? And this is an operation is like a gate, but specific, I mean, to change from one state to another one, I can use one of the available gates, but here we call them operations, okay? And well, suppose that I have the following operations available. I can copy inputs into the cells of the execution trace. This is one of the operations that all the state machines allow. I can sum 2 cells in one row and then leave the result in the next row. I'm going to call this operation add, okay? Then I can multiply by a constant value. For example, I have this operation times 4. I can multiply some cell by 4 and then leave the result in the next row. And then I can multiply, okay? I can multiply 2 cells in the execution matrix and then leave the result in a next row, in a next cell, in a cell of the next row, okay? Yeah, sounds complex, but this is really easy, okay? We see it in the next slide. And then in this, when you are building when you are creating a computation with an execution with a state machine, you need to define which is the shape of your execution trace. In this case, I decided that the shape is going to be with 3 columns. Okay, so only 3 columns. Okay. And you may say, and the rows? Well, we can have more or less rows. I mean, if you use more rows, if your computation is bigger, you will use more rows or less rows, and there is some limit there. Okay, but okay, I'm going to use the term cell or register also. Okay, we use also the term register for each column of this execution matrix. Okay, Then, okay, I decided the operations and the shape of the execution matrix, which in this case is with 3 columns. Now let's do our computation, okay? And remember, our computation is to do x0 times x0 plus x1 times 4, and then times x2, okay? This is the computation that I want to do, okay? So, and my execution matrix would be like this. Okay, the first operation is copy values, okay? I'm going to copy x0, I'm going to copy, maybe this should be, okay. I'm going to copy in A0, which is this cell, I copy the value x0. In my case, I want to do this computation, and the inputs, they're going to be 1, 2, 5, okay? I want to do this computation with these inputs, okay? At this moment, you can imagine that all the inputs are public, but as it happens with what explained for circuits, we can also have private inputs here and public and private inputs, okay? But right now, let's consider everything is public, okay? So yeah, the first thing is that I copy the inputs. So I copy in A0, in this cell, I copy x0. So I put a 1 here, and I copy in B0, I copy x1, which is 2. Okay, so I do this copy. And then I apply the add operation. What does the add operation do? It adds the 2 cells, okay? In this case, adds A and B, and leaves the result in the next cell. Okay, this is what this add operation does. Okay, as you may imagine, I'm just defining the operations and see how to build this execution matrix, okay? But each operation will generate some also some equations, okay, over the execution matrix. It will be more or less the same as before. We are going to have an execution matrix and a bunch of equations, and we will pass this information to the prover, and the prover will generate a proof. Okay, this is the idea. So yeah, I execute the add operation here, which adds these 2 values and leave the result here. And then I just do the times 4 operation. Okay. I'm using the column, I put the 4 here, okay, in column C. Okay, so I multiply this by this and leave the result in the next cell. And in execution matrices, we typically use this idea. I mean, I do an operation and to define the state, to define a value in the next state. Okay, that can be more complex, but this is the easiest state machine. And then I just call them. I use the well. Finally, I copy the 3rd input x2, which is 5, into the B2 cell, and then I call the multiplication operation, which multiplies these 2, and this is the result. Okay. So I have this execution matrix. Okay, this is the execution matrix with inputs 1, 2, and 5, right? With these are the inputs. Okay, and the rest of the values, well, they are the trace of executing this computation. Okay, and executing this computation can be translated into executing a program with these instructions, with add, times 4, and mul. Okay, so we would say that we are executing this program. Okay, from the execution trace, we go to the, I need to define a set of instructions that will define how we compute the execution trace. Okay, typically these instructions is what we call assembly. Many times we call it ZK assembly. Or, well, the first projects, by the way, I work in I have in the university, I have a collaboration with Polygon ZK EVM team that they are building a kind of computation like this. They are building a zero knowledge system to prove executions of transactions in the Ethereum network. Okay, there is nothing private there, but there is succinct computation there. Okay, so we are proving that we are executing transactions in the blockchain, and they are well computed. Okay, the new state is correct.
Is there any link? Now in the second model, I see that there is things that are very similar to multi-party computation. I know that this is a different paradigm, but is there any kind of relation when you are doing things on the blockchain that you have zero knowledge, maybe collaborative work between nodes with multi-party computation?
This is not a multi-party computation because there is a prover and a verifier only.
Yeah, no, I know. Like
Okay.
I say, I mean, like two different models, but I see that, for example, the kind of algebra that you use in multi-party computation
It's similar.
It's very similar. So that's why I don't know if have you seen that there is any kind of a smart contracts that can get profit at the same time of the zero knowledge paradigm, then with multi-party for collaborative? Because I mean, the things that you are showing here in the second part are very, very similar to the kind of language that you can use.
Multi-party computation is used in several places here. I mean, when I said that we, for example, when I said that we compress the circuit into some hash, okay,
this can be done in a collaborative manner with multi-party computation.
Has to be done in a collaborative manner because this hashing, I mean, to generate this hash is not a simple hash. I mean, it's not a hash as it is. It involves generating randomness, creating material from this randomness, and then you need to destroy this randomness. If you don't destroy the randomness, the system is not sound, is not secure. Okay, so but you can do this step and then go give this your material to the next one, and only if one of the parties is honest and destroys the randomness, then the system is secure. Okay, and this is what are called ceremonies. There was a ceremony for the Zcash network, which is another blockchain. So multi-party computation is used there, and also but I'm not sure about this because with homomorphic encryption now they are trying to also decentralize the stuff and then do a multi-party computation I mean, they are trying to split the computation into several parties and so on. These are more advanced scenarios, but well, definitely yes, they are mixing with multi-party computation. I mean, multi-party computation is already used for some parts of it's related with this.
I was thinking the part of secret sharing and of this part, maybe is done with some primitives of multi-party computation here. Taking profit, I mean, you can use the part of secret sharing multi-party computation for some of the stuff that you need to do here, I guess.
Yeah, I would need to talk in a clearer scenario about this, but I mean, yeah, for sure. I mean, but yeah. I mean, here is all the cryptographic machinery appears here. So yeah. Okay, so this is the idea, and well, the thing here is that we can see that there are two different types of columns here. Okay, because I mean, column C, it is going to change. If I ask, column C is going to change for this computation that I am dealing with. I'm doing this computation, right? Column C is going to change if I change the inputs. No, okay. I mean, this 4 is a value that is fixed for the computation that I'm doing, right? Well, these are called fixed columns. Okay, so this is a fixed column. Okay. While the other two, I mean, I can do the same computation, but for other inputs. If I change the inputs, then I put my inputs here, and the execution trace changes completely, right? Not the relationships. I mean, the operations are the same. The relationships that values need to fulfill, they are the same, but the execution trace is different, okay? Because I just put there different inputs, okay? And we call this, but the shape is the same. I mean, but the values are different. Okay, so we call this in the jargon of zero knowledge. These are called witness columns. Okay, so in this execution trace, we have witness columns that change if you change the inputs, and then fixed columns. Okay, which I mark here in the gray color because they are the same, because they are part of the computation that we are doing. Okay. I don't know if we are very sharp with the time. I don't know, Christine. Maybe I have 5, 10 minutes more, or we should finish.
10 minutes.
10 minutes? Okay. Let me finish a little bit this example, okay? Okay, that's it. So the idea here is that well, there is a piece of software here that takes, we call it the executor. In general, in these programs, it is called the executor, okay? And the executor takes the inputs, okay? Takes a program, which are the operations, and then it generates the execution matrix that fulfills, that should fulfill the operations, okay? And this is what we call an executor, okay? Again, I'm not talking about the backend. I'm trying to hide you a little bit the backend, but I'm giving you some ideas of what the backend does, okay? But we have an execution matrix, okay? One of the operations is to take one of these, each of these columns is transformed into a polynomial, and what we do is relationship between polynomials, okay? So, and we need to interpolate these polynomials, okay? Well, the thing is that fixed columns, they are not going to change. So if you need to interpolate this column, okay, you can do it. You don't need to do this per proof. You can do it before, and then in each proof, this column is going to be the same all the time because this is not changing, right? So, okay, so well, the executor has all these fixed columns, and then it has to compute the witness columns. Well, this is per proof, so we need to compute it according to the inputs, okay? And well, the executor generates this execution matrix, okay? And the thing is that the nice thing here is that we can prove with the same system, we can prove different. In this executor, we input the program, the assembly of the instructions of the program that I want to execute are an input of the executor. So we can, here I'm saying that I can prove different, I can prove different computations, different programs, just feeding the executor with different programs, okay? And, but with different programs, but of the same set of instructions, okay? This is the thing. And then, I don't know, we could build this program, for example, okay? X1 plus, this is the program the computation that we were talking about, okay, which is add times 4 mul, okay, but I can do another program, times 4 and mul, and well, it's another execution matrix, it's another program, okay, but in my executor, I just need to change, I give to the executor the correct program, the correct inputs, and it generates the execution matrix, okay? And then, with the program, we also pass the program to the backend, and then the backend generates a bunch of equations that this matrix should fulfill to be correct, okay? A0 should be the input 0, B0 should be the input 1, A1, from the assembly of the execution program, I deduce which are the constraints that I need to enforce into this matrix. And all this information is passed to the backend that a little bit automatically generates a proof for this, okay? But again, it's more or less the same, passing the inputs, passing some equations, some constraints, and then the prover generates the proof in an efficient way using Merkle trees, elliptic curve, and stuff, okay? Yeah.
At some point, that if the computation is right and only if the computation is right, you satisfy this constraint.
Yeah.
How do you, not how, but what do you use to put that? It's the only part that bugs me. Because I can easily say how you can come, you can go from the execution is correct to the constraints, but the other way around, I don't see how you can prove that. Well, how I can be convinced that if all these constraints are satisfied, then I have proved that the computation was correct.
You're not talking about cryptography here. You're talking about, you're not sure that, you think that there is...
I suppose that there is there is some kind of cryptographic hash or whatever that I cannot fake, so that when I receive the proof, I know that these constraints are true.
Mm-hmm.
And the point I cannot.
You're thinking if it is possible that you prove that these constraints are fulfilled and true, and you are proving another different computation and not this one.
But the constraints are fulfilled.
I think this is not possible. I mean, your computation is a set of, I'm defining that this value should be this input. I'm defining that this should be the add of these two. If your matrix, if the execution matrix fulfills these constraints, means it fulfills the program that I'm defining, because I'm just, for each instruction, I am putting its related constraint. So I don't see how you could, if the constraints are fulfilled, the program is well computed. No way to do it wrong, because each instruction will have its associated constraints. We must be sure that we are putting the correct.
I see this way.
You don't see this way?
I don't. Maybe it's because
I think it is bijective, in fact.
It's bijective. If and only if, yeah.
But to be convinced, it's a bit difficult.
Okay. So maybe
you're thinking in a more mathematical way of how we prove that if.
In fact, if you have the description on the left, you will have the right, and if I have the description on the right,
I think they are just equivalent.
At some point, I will have to say that I need this minimum number of constraints to have the objectivity for something not to work. Yeah, because if I have only one constraint,
Yeah. This is one of the main issues here that people sometimes, one of the biggest risks here is that you don't code correctly the constraint of an operation. And then this is a mistake, and then there is a soundness problem here, and you're right, okay? We must be sure that we put enough constraints for each instruction, okay? And this is a very delicate thing, yeah, you're right. And when you are sure that you are doing this right, in my experience, we do this like manually, and then we have some audits, but I don't know if there is some, I don't know if someone from, formal verification here or something like that can assure that this instruction and this constraint, they match. This is your concern. And they are only they're in both ways. This implies this and this implies this, right? We do it like quite manually, doing small operations that we are sure that we are coding right, and having some audits. And I don't know if there is some framework, some theoretical framework to make sure that this is absolutely correct. Yeah, you're right, maybe. Yep.
If your constraints are specific to a given program, that means that they are going to be rejected by the other implementation of the function that you proposed in the previous.
Can you repeat?
In your previous slide, you proposed two programs for the same computation.
No, they are two different computations.
Oh, okay.
These are two different programs, but they are using the same set of instructions. So these programs will generate a set of constraints, and this will generate a different set of constraints, right? But times four, they will, each time I call a times 4, it will generate a set of constraints for this row, okay? And another set of constraints for the other row.
This function, 0 plus x1 times 4 times x2, you can write it in different ways. With different programs. So, for example, you could put first I will multiply 4 on x1, then I will multiply 4 on x0, then I will do the sum of the two, etc. And it will compute 60. That's the first one. But obviously, it will not satisfy the same constraint.
They satisfy different constraints.
So the verifier is going to reject the second implementation, even if it computes the same function.
Probably yes. Yes. Because we should agree on the program. And the program is the set of instructions that we are going to use. So yes. And this is when I tell you that we are proving programs, for example, it is very important that you compile the program with the same version. They are using Docker, I don't know if Docker containers with a certain library, so that the verifier and the prover don't change anything in the optimizations of the compiler should be the same, because we are going to exactly agree on the same program. There can be different there can be many different programs proving the same computation, okay? But we agree on one program. Okay, it's a good question, and this is important. Okay. And essentially, this is what it happens the same. We can have private inputs here. And finally, yeah, these are like, well, I think we already talked about this. And finally, this is like the last slide, okay? And this is what already said, okay? But focus on the machine computation, okay? So we are going to provide to the cryptographic backend, which is the magic here, because we are not explaining too much, but to the cryptographic backend, the executor provides the constraints, the witness columns, the fixed columns, and then this backend is able to generate a proof that is small. Then it takes the outputs from each instruction. We know which things are constant, and it extracts all the publics. And this is what the verifier receives, okay? And says okay or not, okay? Maybe also, if I provide more detail, here we have the verification key, and the backend also needs something that is called the proving key, which is some extra material, cryptographic material, but I wanted to, extract this complexity from the talk. And yeah, finally, summarizing, the idea here is that, okay, zero knowledge has changed a little bit, because now it's much easier for a regular user that is not a cryptographer. One model which is relatively complex is to, okay, give me your circuit, and then I will generate a proof. This was like the first model. And now we are in the area of, give me a program written with a set of instructions, and I will generate a proof for you, okay? Now we have different frameworks like this. I don't know. One famous is SP1 or RISC-0, or, well, TISC is the one on which I'm working now. All of them essentially allow you to write a program in Rust, and then they generate a proof for the inputs that you provide, okay? And they are compiling to a set of instructions that is RISC-V. I don't know if people here is using this RISC-V. Well, they just provide all the constraints for each instruction of RISC-V, and they have a backend to prove. And essentially, it's now very, very easy to use zero knowledge, because you just, well, very easy. You need to write Rust, which is, well, I don't know if it's too easy, but or you can also write C or whatever that compiles to RISC-V, okay? But now it's fairly easy. In the future, it's going to be more easy to just generate proofs for programs. So to arithmetize the problem, I just need to write a program which I'm used to, okay? So, and essentially this is what I wanted to say. Then I had some examples, but leave it for another day, maybe. Okay. I don't know if people online has any doubt, or I don't know. It was too soft, too hard, I don't know. But anyway, thank you so much.
Thank you, José. We can take up a question before we leave.
If anybody wants to ask. Yeah.
Question. So this verifier give okay or no, it's certain or probabilistic?
Is probabilistic, but with overwhelming with probabilities that are in the astronomically small, which means Well, cryptographic, I mean, is 2 to 120 minus 28, something like that. Okay, which means that it's much more possible that some meteorite, crashes the Earth. If we are all dead. That one of these proofs is not sound, or you have the luck. You're lucky, and you can prove something that you don't really know. Okay, so
I think it's a bit like the hash function. The hash function, by
yeah,
chance,
it's the same.
Find
It's the
the
same.
same hash value, but then
We say
the probability is not valid.
Yeah, we say it's computationally impossible, because if you try to do it, the resources that you will need to be successful it's not possible. You need to do a number of operations that are in the number of atoms of the Earth or something like that, which is out of scale. Everything is probabilistic. I mean, cryptography is nothing else than number theory and probability. That's it. I mean, okay. Thank you.